Okay, so all the calculus you've done so far has involved just a function of a single variable. So you've learned how to calculate derivatives, so find the tangents to curves, and also calculate integrals, so you can calculate the areas under curves. Okay, that's all really good, but you'll appreciate that most things in life depend on more than one variable. Okay, so here's an example. Here is the energy of a molecule, and it depends on two angles, the angles at which two different sides of the molecules are rotated. Okay, so the vertical axis of this surface is the energy of the molecule. So as you change these two variables, this alpha and beta, the energy of the molecule changes, and this maps out the surface. So you may want to find the minimum energy of the molecule, or the maximum energy, or something else, okay? And really you need to be able to do calculus in more than one dimension to think about things like this. Okay, so we want to be able to do calculus in more than one variable. So we're going to start with partial differentiation. And we're going to think about the partial derivative of f of x, y with respect to x. Okay, and we define this by, it's a curly d. Okay, so you've probably seen these curly d's before and wondered what they are. So this is what it is. It's a curly d, df of x and y by curly dx. Okay, and I will write this with a round bracket and a y here. And this is defined as the limit of delta x goes to 0, okay, of f of x plus delta x y minus f of x y divided by delta x, okay, and the limits over all of this. Okay, so this is an ordinary, so it looks like an ordinary derivative in x, keeping y constant. Okay, so you have your function x and y, and you change it a little, but you only change x, so it's x plus delta x. You leave y constant. Okay, and this is why I've written this notation. Okay, so some people may just write this as df by dx, okay, or where it's understood here that y is constant, or you can write it explicitly, df by dx with y constant, or an alternative notation, you can just write this as f of x, okay, with a subscript. Okay, similarly we can have the partial derivative of f with respect to y, okay, and we can write this as df by dy, okay, and here we keep x constant. Okay, so this is the limit of delta y to 0, and now we change our function in y, so we have y plus delta y minus f of xy over delta y, okay, as delta y goes to 0. And we can write this in the alternative notation as fy. Okay, so we can think about an explicit example. Let's think about f of xy equals xy squared. Okay, and let's think about what df by dy is. We hold x constant. Okay, let's put it in here. It's the limit as delta y goes to 0 of the function f of x y plus dy. So we've got x y plus delta y squared minus f of xy, so xy squared over delta y. Okay, so this is the limit of delta y goes to 0. Right, and then we've got x times y squared plus x times delta y squared plus 2xy delta y. Okay, that's a cross term, minus xy squared from here. And we divide by delta y. Okay, now you'll see that the xy terms cancel. Okay, we're going to take the limit that delta y goes to 0. So this delta y squared by delta y is not going to survive. Okay, so we're only going to have this one term. So this equals the limit delta y to 0 of, so I'll write this out, x delta y, that's this term, plus 2xy. So as you take the limit delta y goes to 0, this first term goes, like we said. So this is just 2xy. Okay, so that's an explicit example. And we could have just started from here and said we just treat x like a constant. So therefore df by dy with x held constant is just equal to, and we just differentiate this function with respect to y, treating x as a constant. So we just get 2xy. Okay? So that's how it works. Okay, so let's consider a couple more examples. So let's say we have a function of x and y that is x sine x plus xy. Okay, then what is df by dx equal to? Okay, and what we mean when we write this is we want to take the derivative with y held constant. Okay, so if we hold y constant, okay, that y doesn't appear in the first term, so this will just be x cosine x plus sine x, okay, just the product rule. And then we differentiate the second term, keeping y held constant. Okay, so the differential of x is just 1, so this is the result. Okay, if we calculate df by dy, then this means we keep x constant. Okay, and this means if x is constant, this first term goes, and we're just differentiating xy, so we get x. Okay, there's a different example in your lecture notes, so I advise you to study that yourselves. We can also think about functions of more than two variables. So let's have a function u that depends on x, y, and a third variable, z. And let's think about a function x squared y times z cubed plus z sine of x. Okay, so here we can do df by dx, the partial derivative of f with respect to x, means we hold y constant, but we also hold z constant. Okay, so there's three variables now. We have to hold y constant and z constant. So we only vary x. Okay, so we hold y and z constant. So if we differentiate this term with respect to x, we get 2x y z cubed. Okay, and sorry, I'm using two different types of z. Okay. Okay, so if I write this is z, but this is equal to this. Okay, depends what mood I'm in. Okay, so we've differentiated this with respect to x, holding y and z constant. we need to do the same with the second term. So we hold z constant. So this is just z times the differential of sine of x, okay, which is cosine of x. We can do the partial derivative of f with respect to y, and this means holding x and z constant now. Okay, so if we do that, then we get x squared, the differential of y is just 1, and we hold z constant, so we keep the z cubed. And we differentiate this with respect to y, which is just 0. Okay, so that's us. And then we have finally df by dz. And this means we keep x and y constant now. Okay, so we read this, x and y are constant, so we keep the x squared y term. And now we differentiate with respect to z, so we get 3z squared. Okay, and then we differentiate the second term with respect to z, holding x and y constant. So this just becomes sine of x. Okay, so it's just an extension of kind of ordinary differentiation, but you have to just be careful about holding the other variable constant, or the other variables constant. Alright, so if we have a function of two variables, x and y, then what do the quantities df by dx and df by dy actually tell us? Okay, how do we interpret these? Okay, if we think about our function, so this is x, this is y, and then we have the function f of xy on the vertical, okay, which you may want to call z. So let's say this function, the surface is some sheet like this. Okay, so it's some sheet, some height above the xy plane. Then df by dx, holding y constant, means we pick a value of y, and then we see how the function changes along x at that constant value of y. Okay, so if I draw a plane in the x, let's call this z, xz plane, at this constant value of y, okay, this is a plane in the xz, okay, at some y. Okay, and in practice, you know, if you're calculating a number, you want to know what this value of y is. Okay, so we've got this plane in xz, and this plane intersects the surface. Okay, and it intersects the surface. And where it intersects the surface, you get a line, okay? Say line, curve. Curve is better. Okay, so we plot this x, z thing, and where the surface meets the plane, we see this curve, okay? And these are points on the surface at this value, fixed value of y. But we see how the function changes along x as y is held constant. So df by dx as y is held constant is the gradient along this curve. Okay? So if we go back to our molecule that depends on these rotations, alpha and beta, then we saw the surface of energy. So the vertical axis is the energy. So the surface shows the total energy of the molecule, and it's a function of two variables, alpha and beta, these rotations. The red line shows a constant value of alpha. Okay, so that's our plane drawn that intersects the surface, and the intersection of the surface and the plane is a curve, and that curve is shown on the top right. Okay, it's how the energy changes along beta, so how the energy changes as you vary beta for a fixed value of alpha. Okay, if you choose a different value of alpha, you'll get a different curve. Okay, but df by d beta with alpha held constant will give you the derivative of that curve. Hopefully that's clear.